What is a determinant? To answer that, first let's imagine a unit cube with an x vector, a y vector, and a z vector. It undergoes a matrix transformation like this. What does that look like? For the x vector, it is 0 in the x direction and the z direction and is moved 1 unit in the y direction. So that turns the x vector from this to this. That same principle is applied to the other two vectors to get this final volume. The determinant is the difference in area between the final volume and the original volume. Next, now that we know what a determinant is, let's determine it. Taking our matrix from our previous linear transformation, we can delineate it easier by using letters as placeholders for each row, column, space. This, combined with the formula that we have for finding the three-dimensional determinant, will give us our volume change. However, there are two-dimensional determinants showing up in here. What does that mean? Where a three-dimensional determinant is a change in volume, a two-dimensional determinant is a change in area. For these changes in area to be multiplied by a scalar shows what each x, y, or z vector is doing to the final volume. When A and B are 0, those vectors were squished down to plane. They are not contributing to the final volume. We saw this with our parallelepiped earlier, where the only direction that changed and contributed volume to the final shape was our z vector, which is also the only one that contributes volume in the determinant equation. Plugging our numbers into this determinant formula, we get our two zero terms and our one non-zero term, our z vector. And putting that over here, we have our -2 times the determinant of 1, 0, 0, 4 to find the determinant of a two-dimensional matrix. This is what we do. Remember, this is finding the change in area of that two-dimensional shape from a unit square to a parallelogram, which gives us -2 times 4, and our final determinant of a three-dimensional matrix, -8. This means that our parallelepiped is 8 times bigger, but is also flipped from our initial unit cube. A two-dimensional determinant is the change in area that a two-dimensional unit square goes through after a matrix transformation. Seeing that this matrix square turns into this, and if we take a closer look, we'll see what each part of the matrix is doing to each part of the unit square. Finding the determinant then is as simple as taking the full volume of that new square and subtracting out all of the added area to find the volume of that blue rhombus. And what that looks like a little bit closer is our full square minus everything else, giving us this equation, which in a moment you'll see simplifies down to our lovely AD minus BC. Great.